So, welcome back. We have just looked at the Tableau method, and so now let us look at them in action and let us look at some examples. So, we start with a simple example, is this concept satisfiable? So, to say that this concept is satisfiable, what is the concept? That there exists a role filler from the class C, which means that there is some A. So, there is some A new A, it is like a Skolem constant that we had talked about earlier, that there is some A which satisfies this C. So, that goes into the A box and there is nothing else in the T box, because now we have added this Skolem constant or this new variable to A. So, the T box is empty. So, the only rule we can apply is this rule. So, we start by saying that A belongs to this class C. So, what else do we know about A? That it must have a role filler X which belongs to the class C. That is a existence rule. So, from A we have gone to X, both belong to the class C in this case, and no more rules apply. So, we can say that this is satisfiable, that there can be an individual A which will belong to the class C, which is related to the individual A. So, you can always create an individual A and relate it to another individual with a class C. Is there a model for all roles fillers come from the class D? So, again we check for the satisfiability of this formula with a new variable A, add it to the A box, the T box is empty, and so what is the starting point of our Tableau? We have this node A and it belongs to this class for all D essentially. Now, if you remember this rule for all D, it says that for every role filler check that it comes from a class D, but it does not have any role fillers. So, no rules apply, and so we have a model for this statement as well. So, the next example says that is it possible that there is a concept which is made up of the intersection of two concepts. The first one of that says that there is a role filler of class C, and the second component of the intersection says that all role fillers come from class D. So, is there such an element A? So, we add A onto our Tableau, and we basically add this formula to our label set for A essentially. Then we add, so this stands for adding more to the set. So, we already have this conjunction concept in the label set. To that we add these two constituents. There exists a role filler of class C, and for all role fillers we have a class D. So, we first apply the exists rule and we say that create a node X, as you can see here, and say that it belongs to the class C, and this is the relation R essentially. So, we have a role filler called X and we say that its X belongs to the class C essentially. Then to the label set of X we add the class D, because remember that what does the universal rule say, that for every branch check whether D belongs to the class, whether the role filler belongs to the class D or not. If not, add it to this thing. So, we basically add D to this here, and therefore, we have a model for that and it is satisfiable. Is it satisfiable that there exists a role filler of class C and there exists a role filler of class D, and is there such an element which has these two role fillers? Then if you go through this process, you will see that you will start with the sentence, add the two components, then apply the there exists rule twice, and we will create variables here. So, first we will create a variable x, then we will create a variable y. To x we will put it in class C, y we will put it in class D. So, x belongs to class C, y belongs to class D, and lo we have a model. So, that is satisfiable. So, here is an example that we had mentioned earlier. Given that Lucy likes apple, we know this, Lucy likes apple, and we do not know anything else about Lucy. Can we conclude that Lucy likes fruits? Of course, we should know that apple comes from the class fruits. So, given that apple is a fruit and given that Lucy likes apple, can we conclude that there exists a fruit that Lucy likes? So, this is given to us that A is related to B and that B comes from class C. Can we entail that A belongs to the class of those things where there is a role filler of class C essentially? So, we will add the negation of this here and show that it is unsatisfiable. So, when we take the negation of that, then what we get is this, because the sign of the quantifier changes. And now, what do we have? We have A here, which has this property which we got from the negated goal, that all role fillers do not come from class C, or all role fillers are not in C. We also know that A likes B, let us say R stands for likes, and B actually comes from the class C essentially. So, when we apply this rule, then for every branch, so we have A which is Lucy and we have B which comes from class C. The universal rule says that for every branch you add whatever is here. So, we add this here, not C we add. So, this becomes our set which is shown here, and this of course is closed. Why? Because you cannot belong to the class C and not belong to the class C. So, this slide sums up this whole process. Therefore, from the given information we can conclude that Lucy likes fruit. Can we conclude from the same example that Lucy likes only fruits? And that will translate into that everything that she likes is a fruit. So, the universal statement that everything that likes the fruit, and Lucy belongs to that class of people or individuals who only like fruits. So, this stands for only in some sense, only fruit, and that is a query that we have. So, does our knowledge base entail this essentially? So, as before, we will take its negation and add it to that and then try to show that it is unsatisfiable. If it is unsatisfiable, then the entailment holds, remember that. So, we have added that negation of that, and that will translate into this. So, now we have the label set for A contains this has come from the negated goal, and we also know that there is an element B which already exists, and it comes from the class C that is stated in the knowledge base itself, and that A is related to B by the role filler R, role R essentially. Now, we have got this rule in the label of A. So, we expand that rule. What does the rule say? That there exists something which is of not class C. So, what happens there? Then we create a new variable x and we say that this is not in class C. That is the existential rule, and at this point there is nothing else we can do. So, we terminate and we have a model. So, it means that the original sentence that she likes only fruit is not a conclusion we can make. So, we cannot conclude that Lucy likes only fruit. So, this slide sums up this whole process. So, here is another example. C is subsumed by D and there is an element in the domain at least that is expressed by the fact that there is an element which belongs somewhere in the domain. Does it entail the fact that there is an element who has a role filler from the class C, and that also is that also comes from the set of elements who have a role filler of class D essentially. We already know that C is subsumed by D essentially. So, everything that comes from the class C must also belong to the class D essentially. So, intuitively you should recognize that this statement should be true. So, that is the knowledge base that is given to us, that is the conclusion that we want to draw, and we negate the conclusion as before and then try to show that it is unsatisfiable. And when we negate it, as we can see here, we will push this negation inside and we will remove this and replace it by this, but once the negation gets pushed inside, then this will translate into there exists C and for all R not D. So, that is in our T box now. This comes from the fact that C is subsumed by D. Remember that this is how we translate it, and this is the negation of the goal that we wanted to prove. And the A box has only, it says that there is some element called A. So, we start with A in the tableau and it only says that okay, there is top there. Then we apply the T box rule, which basically means we first bring this one and add it to this set here. Remember that there is still another sentence in T box still remaining. We will add that later. So, having added this, then we apply the conjunction rule and add the individual elements here. Then we have an existential statement and a universal statement. So, first we apply this existential statement. So, we create this x and we say that x is from class C essentially, and x is related to A by the role R essentially. Then we apply the universal rule. The universal rule says that for every edge that you can find going from any element in the domain, add not D to the role filler. So, to this we add not D. So, that is what we know about x at this moment. Why C? Because we said that there is a role filler with class C, and why not D? Because we say that all role fillers are from not D. So, that is what we had. We had this in the label set of x. Now, we bring the other T box statement here by applying the T box rule here, and we will create two branches now, one going this way and the other going that way. In one branch, we will add not C, and as you can see, this not C will clash with C, which is already there in the label set of C. Remember that this stands for you are adding to the label set. So, C was already there, now you added not C. So, that branch is closed, this branch which has C and not C is closed. In the other branch we added D here, but there was already a not D in the root of those two branches. So, this branch is closed because we have not D and D. So, both the branches are closed and there is nothing else we can do. So, therefore, this is entailed. This is what we set out to do. Here is another example with the same starting point, that there is one element in the domain at least. Does it entail the fact that if every role filler comes from class C for every element which has this role R, then there exists at least one role filler which comes from class C. So, if you remember, this is a universal statement, it can be vacuously true, which means that this entailment should not really hold essentially. So, but let us see how that happens, because this says that there exists at least one essentially. So, greater than or equal to one role filler, whereas this can be 0. So, obviously, it will not entail that, but does the logic work out? That is the question. So, this is what we want to show, and therefore, we show that we add the negation of that what we wanted to show to this thing. Our A box is as before only contains the fact that there is an element in the domain. Our T box contains this thing here, which when we push the negation sign inside and replace this with a concept forming operator, we get this thing as before. So, that is what we have. We started with the empty concept set, in the sense that, or the top concept set rather, and then we apply the T box rule, add this to here, that is an intersection. So, we add the two individual elements here. And what is this saying? This is saying that every role filler must come from class C, and we are talking about the element A here. Every role filler must come from the class C. The other statement is saying every role filler must come from a class not C essentially, but there is no role fillers here. So, it is not that we are asserting the existence of a role filler. The rule says if there is a role filler, it must come from class C, but since there is no role filler, no more rules apply, and as you can imagine, we have a model for the negation. So, this is what is happening here, that we cannot entail this statement. So, here is a little bit of a situational sentence. We have landlords own houses, which we have expressed as saying landlords come from the set of house owners. Those who own taxable items, whatever they are taxpayers essentially. So, if you own taxable items, then you must be in the set of taxpayers. Houses are taxable, Jack is a landlord. Houses come from the set of taxable things, and this is an A box statement that Jack is a landlord. Does it entail that Jack is a taxpayer? Again, it looks like it should be the case, but let us see what the Tableau method tells us. So, this is just a restatement of the problem. This is the query, and we have removed those big words and replaced them with small words here. So, L stands for landlord, O stands for ohm, H stands for house, B stands for taxable, because we can't put T there, T stands for the top concept, remember. P stands for taxpayer essentially, and we have said that Jack, with A stands for Jack, Jack is a taxpayer, and does it show Jack is a landlord, and does it show that Jack is a taxpayer. So, again we add the negation of that to our knowledge base. So, that is what we have added the negation to that, and we want to show that it is unsatisfiable. What does the A box says? A box says that Jack is a landlord, or A is an L, let us just use that phrase now, and A is not a P, or Jack is not a taxpayer. This came from the negated goal, and this is from the knowledge base. So, the A box has two things, which is what we start with here, that the label set of A contains L and not P, and the T box has everything else that we know about the knowledge base, that landlords are house owners, and if you own something which is taxable, you have to pay tax, and houses are taxable. That is the third statement in that. So, we will add them one by one to the tableau. So, the T box rule. So, first we have added this one here. This is a union statement. So, we will create two branches L 1 and L 2. In L 1 we will add L, not L, or complement of L, and in L 2 we will add that there exists an OH essentially. So, so this stands for landlord, then there, and this stands for house owners, if you remember. So, of that the first branch L 1 has L and not L. L not L we added here. L was originally in the knowledge base. So, that branch is closed. So, we are left only with the second branch. So, we are in the second branch now with A, and we have this L and not P there. And there exists that we have house owners essentially. So, this exists thing we apply the existence rule, and we say that we will create a new branch, new node X. So, this is A, remember that A stands for Jack, and this is X, and X is a house essentially, and O stands for owner, if you remember. So, the relation is O and X is a house. Then we apply the T box rule. We have got the second element from the T box, which is here. That is a union statement. So, again we split this L 2 into three branches, L 3 and L 4. In one we add P, and in the other we add the remaining part, which is not O, for all O not B essentially. So, this P and not P in branch 3, they cancel each other, they clash, and therefore, that branch is also closed, and we are left with only one branch, which is L 4. So, we are now in this L 4 branch, and we have this statement, there exists a house owner, there this thing, and all owners are not taxpayers. So, anyway, you can keep track of the meaning of those things. So, we apply this rule first. This rule says that you add to whatever labels you had the label of not B essentially. So, what do we have now? The label we had H here, and we have not B here essentially, because we added this not B because of the universal rule essentially. Then again we apply the T box rule, and we are left with that last statement there, not H or B. So, we add that here. remember this stands for addition. So, we have not written the full thing, but whatever was there plus this essentially. We create, because this is a union rule, we create two branches L 5 and L 6. In L 5 we add not H, and in L 6 we add B essentially. Now, you can see that not H is clashes with H, which is in the parent of that, and B also clashes with not B essentially. So, both the branches L 5 and L 6 are closed essentially. So, branch 5 is closed, branch 6 is closed, and therefore, there is nothing else we can do. So, yes, this is true. So, we can conclude that Jack is a taxpayer. So, description logic is a family of languages. Each language strikes a balance between expressivity and computational complexity. Inference problems are posed as satisfiable problems, and the Tableau method is used to solve these problems. OWL 2 supports this particular language SROIC that we had discussed earlier, and you can use a freely available tool called ProTeach for using OWL. Now, there is one thing I want to say before we close, which is that we now have a procedure which is the Tableau method for determining whether C is subsumed by D or not. So, we can answer this question, that is it true that C subsumes D. Now, given this procedure and given a set of concepts, we can arrange them in a taxonomy. So, if there is a concept C 1 and this C 1 is subsumed by, let us call it C 2, and this C 2 is subsumed by C 3 and so on, and maybe C 2 has another child C 5 and C 5 also is a child of some C 6. So, such arrangement of concepts is called a taxonomy. All you need to arrange the concepts that you have in a taxonomy is a procedure which will answer this question, that is a concept subsumed by another concept, and once we have this procedure, we can construct a taxonomy. This process is called classification. Or there is a process called classification, which tells you that given a taxonomy and you have given a new concept, where do you place it in the taxonomy. We will defer that when we look at taxonomies in more detail a little bit later, and then we will look at this algorithm for classification as well. So, we will end our study of description logics here.